Hey world, welcome back. Today's episode is based on the paper Mirror Mirror on the Wall, Have I Forgotten It All? A new framework for evaluating machine unlearning by Brennan Brimhall, Philip Matthew, Neil Fendley, Inji Chow, and Matthew Green, published in 2025. Machine learning models often rely on massive datasets scraped from the web, purchased from private sources, or collected directly from users. These datasets may include copyrighted, inaccurate, or even illegal content such as CSAM or poisoned examples and can expose sensitive information. Legal frameworks like the GDPR, DMCA, FCRA, and HIPAA provide rights to delete or correct personal data, but retraining a model from scratch to remove offending data remains prohibitively expensive. Machine unlearning aims to remove traces of specific data without full retraining. This paper makes three main contributions. It introduces computational unlearning, presents empirical evidence that existing unlearning methods are distinguishable from fully retrained models, and derives theoretical implications about the limits of unlearning. Computational unlearning is defined as the inability of any probabilistic polynomial time adversary to distinguish between a model unlearned on a forget set, denoted d sub f, and a control model retrained on d minus d sub f, except with negligible advantage. The authors formalize this via cryptographic-style games in both white box and black box settings, where an adversary receives two models, one unlearned, one control, in random order and must guess which is which. Success beyond 50% plus a negligible function negl of lambda indicates a failure of the unlearning method. This definition captures adversarial capabilities and enforces indistinguishability as the gold standard of forgetting. They construct two distinguishers. MAA score uses membership inference attacks to measure whether a model still leaks membership signals for the forget set, and KLD score sums the Kullback-Leibler divergences between model outputs on noisy variants of the forget set. Higher MAA score and KLD score values on unlearned models reveal residual traces of the forgotten data. Experiments use ResNet 18 models trained on CIFAR 10 for 50 epochs with stochastic gradient descent, momentum, learning rate 10 to the minus 2, batch size 512, and weight decay 5 times 10 to the minus 4. 3 heuristic unlearning methods, bad teacher, amnesiac, and selective synaptic dampening, SSD, and 1 approximate method, certified deep unlearning, CDU, are evaluated. SSD uses a dampening constant of 1 and selection weighting of 100, while CDU employs a noise parameter sigma derived from epsilon and delta in projected gradient descent. Forget set sizes vary from 10 to 1,000 examples. Adversary success rates exceed 60% for all sizes and both distinguishers, rising toward 90% as the forget set grows. When forgetting an entire CIFAR 10 class of 5,000 images, adversaries achieve 100% success. Varying sigma from 10 to the minus 5 up to 10 to the minus 1 shows KLD score increasing exponentially with sigma, confirming that even DP-based methods remain distinguishable at any practical noise level. Next, the paper categorizes unlearning methods. Heuristic methods lack formal guarantees. Approximate methods rely on differential privacy or certified removal, and exact unlearning uses model checkpointing and retraining. Score-based evaluations like accuracy gaps and membership inference are intuitive but insufficient, as they permit over-unlearning, unlearning inversion, and forgeability attacks. Theoretical results show that deterministic unlearning cannot achieve computational unlearning for entropic learning schemes such as stochastic gradient descent. Only perfect unlearning, producing exactly the same model as retraining, would suffice for deterministic methods. Conversely, randomized unlearning is necessary but not sufficient. Differential privacy can in principle satisfy computational unlearning if epsilon and delta are set to negligible values in the security parameter lambda. However, such tight bounds collapse model utility to baseline levels, meaning the unlearned model performs no better than random initialization. The authors prove that if an unlearned model is indistinguishable from a control, its utility must be equivalent as well, leading to an extreme privacy-utility trade-off. Most current unlearning methods are deterministic, SSD, amnesiac, and certified removal, and therefore doomed to fail the computational unlearning definition. Randomized methods like bad teacher and DB introduce some hope but still leave distinguishable artifacts. Certified removal bounds parameter differences between models but does not guarantee uniform distribution within those bounds. Given access to the original model, an adversary can exploit directional divergence to distinguish unlearned models. The authors suggest future directions including relaxing adversary capabilities by restricting access to the original model or limiting query counts, exploring unlearning for generative models where discrete concepts must be forgotten, and investigating unlearning during fine-tuning of foundation models. In conclusion, computational unlearning reframes forgetting as an indistinguishability problem. Current methods do not meet this rigorous standard. Deterministic unlearning is impossible without perfect replication of retraining, and differential privacy collapses utility when pushed to oblivion. Designing truly forgetful models demands new randomized approaches that achieve indistinguishability while preserving performance.